Hello, my name is Ines Pagan, and I'm a toxicologist at the U.S. Environmental Protection Agency. This is the Risk Characterization module of the Air Toxics Assessment course. In this module, we will talk about risk characterization, which is the last part of the risk assessment process. Going back to the detailed air toxics risk assessment process, it is divided into four main parts: the planning and scoping process, the exposure assessment, the toxicity assessment, and the risk characterization, which is our topic for this module. In the risk characterization, we combine exposure analysis and toxicity information to make statements about how risky those exposures are and how uncertain we are about our estimation of risk. So what is the risk? How do we characterize risk? In this step, the risk assessor combines information about how people are exposed to chemicals together with information about toxicity of the chemicals and makes qualitative and quantitative assessments of how risky those exposures are. An important element in this part of the risk assessment process is a clear description of the major uncertainties in the risk assessment as a whole. This gives the risk manager an idea of the magnitude and the direction of the uncertainties associated with the risk estimates. Uncertainties are generally described qualitatively. However, in some cases, uncertainties can be characterized quantitatively depending on available data. As we combine information about toxicity and exposure, we must remember that people can be exposed to different chemicals by different pathways. The risk assessor must track all of this information and present it in a clear way so the reviewers and risk managers can easily see what chemicals are causing what risk by which pathway. This certainly helps them in their decision on how best to reduce the overall risk. To do this, the risk assessor will generally show tables of risk for each chemical separately, the sum of the risk of the chemicals in each pathway separately, and finally, the sum of the risks that a person has through all pathways when appropriate. The process is a little bit more complicated than that, but that's the gist of it. So here's an example of a single chemical released from a single facility that makes its way to the air you breathe and the beef you eat. For each pathway, you have to assess the exposure, identify the toxicity associated with each route of exposure, calculate the risk for each pathway, and then sum across all the pathways to get the total risk, if appropriate. And again, risks across exposure pathways would be added only when appropriate. For example, it is not appropriate to add results of a screen with results from a refined risk assessment. That would be like adding apples and oranges. For air toxics assessments, we will always look at the inhalation route. Risk characterization for other pathways will only be done for a limited number of hazardous air pollutants, or HAPs. These chemicals tend to persist in the environment for a relatively long period of time and can accumulate in living tissues by a process called bioaccumulation. Now, before we go into the calculation of risk, we will review a few important points to consider for both cancer and non-cancer assessments. Cancer risk and non-cancer hazard are calculated separately from one another. This can be confusing sometimes because some chemicals can cause both cancer and non-cancer effects. We normally go through the entire process twice. First, we calculate and present risks posed by cancer-causing chemicals, and then next we calculate and present hazards posed by chemicals of interest. Now that we have a good idea of the basic process, we will go into more detail on how to calculate inhalation cancer risk. We can calculate cancer risk of breathing a carcinogen in the air simply by multiplying the concentration of the chemical in air times its inhalation unit risk. Note that the units in the formula shown here cancel out to give a unitless answer. The answer is a statistical probability. In the example shown here, we can calculate the inhalation cancer risk of a chemical X by multiplying the exposure concentration of chemical X, which in this case is 1 microgram per cubic meters, times its inhalation unit risk, which is 2 times 10 to the minus 3 per microgram per cubic meter, and the result is unitless. What happens when we breathe air that contains more than one carcinogen, which is often the case? When this happens, you calculate the risk posed by each chemical independently and then add them together to get the total cancer risk. It is that easy. So what does the risk result mean? The risk you calculate is the excess risk of an individual person has of getting cancer over their lifetime because of that, and only that exposure. It is important to note that you can get cancer for many reasons. For example, genetic predisposition or lifestyle choices such as smoking. We're only looking at the excess risk you have from exposures to air toxics. So the cancer risk is a probability of an individual getting cancer because of the exposure. The result is the excess risk to an individual at the point where the exposure concentration is either measured by monitoring or estimated by a model. The population at risk, on the other hand, is the number of people that are living at a specific risk level. For example, if you use modeling to estimate exposure concentration at the census block centroid, all the people in that census block are described as having the same risk. And just because you calculate risk of getting cancer does not mean that you or anyone in that population will necessarily get cancer. The risk results are estimates with lots of conservative assumptions built in. They're not absolutes. So now we'll talk about the inhalation non-cancer hazard. We calculate the inhalation non-cancer hazard in a similar way than we do cancer risk, except that we divide the concentration of the chemical in air by the reference concentration. Note that the units in the formula shown here are commonly given in milligrams per cubic meter. So the answer you get is called a hazard quotient, because it is a quotient that is an estimate of hazard. The hazard quotient is a simple comparison of a chemical's concentration in air to a safe reference level. Let's see an example. In the formula shown here, we calculate the non-cancer inhalation hazard of chemical X, which causes liver toxicity, by dividing the concentration in air or exposure concentration by a reference concentration, which is a level in air considered safe to breathe. Just as in the case of cancer, we can have multiple chemicals in the air we breathe that can cause non-cancer effects. And just as with the case of cancer, we can calculate the total non-cancer hazard by adding up all the individual hazard quotients. The result is called a hazard index, or HI. If the HI is greater than 1, we may have a problem. A quick look at the individual hazard quotients can tell us right away which chemicals are causing the most problems. So what does this mean? The hazard quotient, or HQ, is a simple comparison of a chemical concentration in air to a level below which there's no adverse effect. The hazard quotient is not a unitless probability like a cancer risk is, and for this reason we cannot add cancer risk in non-cancer hazard. In addition, a hazard quotient above 1 does not necessarily increase linearly as the ratio increases. Here's another difference between cancer risk and non-cancer hazard. For cancer, we don't make presumptions about the different types of tumors we may observe, and we just add them all together and leave it at that. For non-cancer effects, however, we can sometimes disaggregate the initial HI into target organ-specific HIs. We only do this for chemicals that affect the same target organ or act by the same mechanism of action. This analysis is called a Target Organ Hazard Index, or TOSHI, approach. This should only be done by a knowledgeable toxicologist that is familiar with this approach. Ultimately, the toxicologist will decide whether one can reasonably separate an initial HI into separate TOSHIs. So what do the hazard answers mean? Just as with cancer, HQs are estimates of hazard to the individual at the point where the exposure concentration is either measured or modeled. Population hazard, on the other hand, is an estimate of the number of people living at a given hazard level. We said earlier that we focus in the inhalation pathway when conducting air toxics assessments. However, we recognize that some hazardous air pollutants may deposit out of the air and can result in potentially dangerous levels in other media, such as soil, water, or food. As described earlier in this presentation, we only evaluate hazardous air pollutants that persist in the environment and may bioaccumulate, such as mercury and dioxin. The risk analysis for non-inhalation pathways is usually more complicated than the inhalation pathway, and we usually rely on modeling to do this analysis. We don't have toxicity information for all chemicals, so what do we do in this case? When there is no toxicity information, there are several options. Some of these options are better than others, depending on the circumstances. Sometimes we just omit certain chemicals from the risk estimates, and then we discuss why we did this and the uncertainty that is associated with this. Sometimes we can use the known toxicity of another chemical as a surrogate for a structurally similar chemical with no toxicity data. In some instances, individual chemicals in a class, such as dioxins, are given a toxicity value that is scaled to the toxicity of one of the chemicals within the class. These scaled values are called toxicity equivalency factors. A qualified toxicologist should be consulted to do such evaluations. So how correct are our risk estimates? One of the most important parts of the risk characterization is to provide a thorough analysis of uncertainties associated with each major part of the risk assessment. It would be ideal to state the direction and the magnitude that the uncertainty is likely to have on the risk estimates. This analysis is qualitative in nature, but can be done quantitatively in certain circumstances. When done qualitatively, it is often done in a narrative fashion and based primarily on the best judgment of the analyst. Risk managers need to have a good idea of how correct the risk estimates are in order to do their job. If the risk analyses are too uncertain, the risk manager may determine that nothing can be done based on the risk assessment as is. In such cases, the uncertainty analysis may help point out areas that could be made less uncertain to substantially improve the quality of the risk estimates. A few important areas to consider in an uncertainty analysis are, for example, how sure are you that people are actually being exposed? Did you use the best air dispersion model? Did you have good emissions inventory input data? What about the chemicals not included in the modeling analysis? Because we don't have any known emissions, but monitoring shows that the chemical is present. What about all the uncertainties associated with the toxicity data? We often use animal data to estimate human toxicity. Is that likely to under or overestimate the risk? What about the chemicals that we modeled, but for which we have no toxicity data, as we said before? What if we're using a surrogate toxicity value? All of these and many more reasons must be critically discussed in the uncertainty analysis. The analysis must try to give the risk manager a sense of the magnitude and direction of the various uncertainties. Ultimately, the risk manager must be able to decide if the risk information is of sufficient quantity and quality to make critical risk management decisions, or whether specific uncertainties need to be reduced before decision-making can proceed.